Hi everyone, Mr. Revetto back for lesson 2 of Unit 9, where it's our first of a couple units in trigonometry. Today's lesson is going to focus on the unit circle. So just to recap, in lesson 1, we introduced, or really reintroduced to us, the three basic trig functions, sine, cosine, and tangent, and remembered how to use those to find the lengths of different sides in a right triangle, but just based on their definition here. Today we're going to talk about the unit circle, which is going to help us find more exact values of the trig functions and understand them a little bit better, but we need to come up with a sort of common language before we can move on to there. So, as you may recall, the coordinate plane is broken up into 4 quadrants. I mean, we just have the simple crossing axes there, and there's the 4 different areas there, and we label those. We have a common labeling system just so we can easily understand where we are here. We start with the first quadrant where all the coordinates are positive. And what we mean by that, again, a coordinate plane is an X and a Y, right? An X comma Y. We mean the X is positive, which means we go to the right, and the Y is positive, which means we go up, right? And we'll recall that how far to the right of the Y-axis you are is exactly what the X coordinate means, right? It's how far away to go. And the Y coordinate is exactly how far above or below the x-axis you'll go, right? It's a measure of your height there. So we move counterclockwise then, starting in this first one where all are positive. So this is quadrant 1. Moving counterclockwise, I mean going to the left if you're thinking of a circle, right? So we have quadrant 1, then quadrant 2, 3, 4. Okay, and counterclockwise is going to be the standard for everything with an angle. We always, that's sort of the standard position. We move counterclockwise around it here, and that's going to be important in just a moment. We'll see here. So we'll just recap with a definition here that an angle, recall from geometry, is a set of points that's the union of 2 rays here, which just means we basically have 2 lines. So that's still true here, just like it is in geometry, except when we study angles on the coordinate plane here, one of the rays is always going to be the positive x-axis. So that's going to be scrolling down to here, the initial side, like on this diagram. This is one of the rays we're having. And the terminal side is where the angle ends here, and that's what we call standard position. We'll see what that means by where the angle ends in just a second. But just taking a sneak peek at this little sketch here, we can see that angles, we sort of measure from this side, and we go around that many degrees of whatever the angle is, and then we end up on what's called the terminal side there, okay? Unlike in geometry, however, where angles we only measure up to 180 degrees, on the coordinate plane, there's really no limit to angle measure. We can have angles from 0 up to 360, which is a full circle, but we can even go beyond that, like we see in this little example here at 390 degrees. We can even actually go have negative angle measurements, which we'll understand what positives and negatives mean from this example in just a moment here, right? But there's no limit to what the angle measurements can be. They can be any number, positive or negative. But there are a couple of special angles we're going to want to keep track of because they sort of help situate us where we are on the coordinate plane, or like where an angle ends up here. Those are known as the quadrant angles here. So the quadrant angles are 0 degrees, which is right over here. We haven't gone anywhere from the initial side here. 90 degrees, which means starting from the x-axis, we go exactly 90 degrees to the y-axis, which should make sense to us because, again, our x and y axes are perpendicular to each other, and perpendicular means there's a right angle between them, right? So we have 0 degrees, 90 degrees as it's labeled up here, then 180 degrees, 270 degrees, and 360 degrees. Those are known as our quadrant angles. We always go measure counterclockwise when we have like a positive angle measurement here. It's sort of related to that sort of standard notation we're talking about. A positive angle, we start on this initial x side and we go around. So around counterclockwise. So if we look at this first inner one, 30 degrees, well, we start here, we go out 30 degrees, and that's our terminal side there, okay? And it's always, so our quadrant angles, again, they just sort of split it up into the 4 quadrants, and it's always just where the angles are here, and it's broken up by 90 degrees. We basically split a full circle up into 4, quadrant 4, right? So like I said, standard position is, the standard notation is that a positive angle goes counterclockwise like that, but you can also have, like I mentioned, a negative measure here, and in that case, we're gonna measure the angle in the clockwise direction. So instead of going left around the sort of axes here, we go right or just clockwise. Okay, so in that example, we can see from this angle here, the negative 330. We start at the initial side again, but it's negative 330 degrees. So we'd go around negative 330 degrees, and we have the same side here. But you may have noticed then from those two examples that both 30 degrees and negative 330 degrees have the same terminal side. And because our angle measurements can take any sort of number here, we're going to run into this situation sometimes where two angle measurements have the same terminal side. And what we call those are coterminal angles, like it says down here. That's angles that in standard position have a common terminal side, just like we were saying. Right? And that comes from the fact that if we just think about it, a circle only has 360 degrees. Like once I go around once, I've gone 360 degrees. But I could go more than that, like in this example, 390 degrees. I can go a full 360 degrees, a full circle around, and then an extra 30 degrees, right? So actually 390 degrees is also coterminal with 30 degrees and negative 330 degrees. There's going to be plenty of coterminal angles. They're really kind of just multiples, like we would just add and subtract 360 around, because we could just keep going around the circle, right? If I went around the circle twice and then another 30 degrees, that would also be have the same terminal side. It would be coterminal with all of these here, right? But the key takeaway is we take our measurements, positive angle measurements, we start here and we go around to the left. Negative angle measurements, we start here, we go around to the right, okay? And those quadrant angles are always going to help situate us and figure out where they are. So let's just get some practice with that so we understand. In these, we want to draw a little rotation diagram and identify the quadrant that the terminal ray falls in. So in order to do that, we need to actually draw our quadrant or axes here. And we have theta is equal to 145 degrees. So whenever you're trying to figure out where an angle lies in the coordinate plane, you always have to think of your quadrant angles and just understand sort of where 145 degrees falls. Our quadrant angles are, again, 0 degrees, 90 degrees, 180 degrees, 270 degrees, and back up to the original of 360 degrees, right? So just think about it, 145 degrees, that's greater than 90 degrees. So it means I'm gonna have to start over here, go around at least to that point. And now we're just sort of getting a rough idea. It doesn't have to be exactly perfect. We just want to know where this falls, because as we're going to see later in this unit, knowing exactly which quadrant it's in is going to be very important for getting the correct answer here. So just think, is 145 degrees greater than 180? Do I have to go past that second, the negative part of the x-axis there, or not, right? And of course, 145 degrees is less than 180, which means I'm not going to go all the way up to 180. I'm just going to go a little bit further, like somewhere over there, okay? And we'll draw our terminal side, and this is our angle theta then. That's our measurement of angle theta. And the terminal side ends up in the top left quadrant, which we recall from above is quadrant 2, right? Because they go 1, 2, 3. They go 1, 2, 3, and 4. Okay? So let's practice one more here. Like we can also have 200, like over here, 72 degrees in number 3. Let's try that one. Okay, well, again, just think about your quadrant angles. We start 0 degrees, and the next sort of checkpoint is 90 degrees. 72 is less than 90, which means I'm just over here somewhere. Okay, that's my angle, which is just in quadrant 1. And so when we have angles that are just between 0 and 360, it's really easy. We just sort of count around, we go around and count it, right? But we can also have, like we saw, a negative angle measurement, like we have in, say, number 6. Let's take a look at that one, just so I have a little room to draw it, right? So looking at number 6, the angle measurement's negative 310 degrees. Well, it's going to be the same idea, but the only thing we have to remember is that negative means, again, we start on the positive x-axis and we go around to the right this way. But we still want to use those quadrant angles as sort of our checkpoints and our guides, just sort of in reverse now. So remember, each time you go and you hit the other axis, you've gone another 90 degrees. It's the same idea if you go this way. It's just you've gone negative 90 degrees, negative 180, negative 270, negative 360, right? So in number 6, negative 310 degrees. Well, that means I go backwards, so I got to go at least 90 degrees. Negative 310 is more negative than negative 90. I got to go up to 180. I got to go even further than that. I got to go to 272. Right, and 310 is a little bit more negative than negative 270, right? It's because we've got negative 270 degrees, or 3 quadrants now, but it's not quite 4 full quadrants. It's not as negative as negative 360, which is all we go here. So if we just go to that point, we'll have negative 310 degrees, right? And that's our angle theta in this case, which just ends up in quadrant 1. So we can think about it like that, but if we can't figure out if we can't sort of reason out those quadrant angles in reverse, the other strategy we can have since we have this idea of coterminal angles coming from the fact that there's only 360 degrees in circle, right? And you're just going to keep going around them. The strategy is that whenever we have a negative angle measurement, we could always just add 360 degrees to this until we get a positive value, because that's going to have the same coterminal, it's going to have the same terminal side there. They're going to be coterminal, as we just saw above. If you go around the circle one time, you're going to have the same, which means if you add 360 degrees to your measurement, or if you even subtract it, you go around the circle backwards, you have the same terminal side. So we would get, in this case, just 50 degrees. And in that case, well, 50 degrees is less than 90, so we would end up like that, sort of, right? And it's the other way we can think about it to figure it out, if we just need to know where we are. And a similar idea even for like number 7 here, 460 degrees. Well, we could easily reason that out with our quadrant angles, meaning I have to start over here. It's a positive thing, so I'm going to go around to the left or counterclockwise now. I can start here, then I'll go around 90 degrees, 180, 270, up to 360. And now that I've gone 360 degrees, I've got another 100 degrees to go, right? So going up to the next quadrant, that's another 90 degrees, but now I have another 10 to go. I'm just sort of keeping track in my head here, right? Which ends me up right over here, right? So in this case, the angle ends up in quadrant 2 again, right? But just like we could sort of add 360 to the negatives, if we have any values that are over 360, like we saw though, that just means we're sort of going around the circle once and then seeing what's left over. So why don't we just sort of take out that 360, and we see that it's 100 degrees like we saw. Well, 100 degrees, now we know how to do that. That's just you go up one quadrant. Let's switch to the pointer for this. I don't want to mess it up. So we would go up one quadrant and a little more, but that's just exactly what we did. It'd be the same idea for number 8, but if we added 360 here, we would just get negative 40. You could just add another 360, right? Or again, you can sort of follow those quadrant angles and remember that each time you come across the axes again, you're going another 90 degrees. So now that we've gone through that and we sort of understand how to measure angles and view them on the coordinate plane here, let's talk about the unit circle here. So the unit circle is a circle that's centered at the origin with a radius of 1 unit. Its equation is just x squared plus y squared equals 1. And that should make sense because if the circle's 0, 0, remember we have that standard form of the circle, x minus h squared plus y minus k squared equals 1. Well, h and k are supposed to be the center of the circle. They're just 0, 0 for the unit circle. So it's just x squared plus y squared. And it's equal to r squared. That's our standard form of the equation. Let me just write that down for us, right? Plus y minus k squared equals r squared, right? And what I was saying is the h and the k, they're just 0 here. And the r, since its radius 1, is 1 unit, right? Or 1 squared is just 1. So that's the equation here. But really, we want to understand how to use it. So considering the fact that the radius is 1, let's label the coordinates where the circle hits each axis, okay? So it's easier here with a little picture where we have this point P. Let's examine the right triangle formed by an angle inside the unit circle and a perpendicular segment drawn to the x-axis from where the terminal side here. So let's say point P has coordinates x comma y over here, right? That's some point on the unit circle in this case, and we want to label the coordinates where the circle hits each axis. So we want to fill in the ratios of sine of theta equals O over H, right? So, cot, and TOA. Well, this is the triangle we have. Here's our little angle theta, right? And here's the triangle that we can set up from it. If we draw a line straight from the origin to the point P of radius 1, that's exactly what our unit circle is, right? It has a unit 1. This is, of course, our hypotenuse, right? And then the other thing we have to figure out in this triangle, if we want to figure out what sine of theta and cosine of theta are, what are the measures of these two sides? Well, of course, this vertical side is the opposite one to this angle, right? It's not touching it, it's away from it. We need to figure out what is its measure if we want to figure out what the sine is. But let's, again, think about what point P having coordinates x comma y means. Well, that means that we would go starting from the origin to the right x units, or if it was negative, it would be to the left, but we go to the right x units and up y units, right? But in terms of this triangle, all that means then is that this triangle, this vertical side of the triangle has side length of y, right? And similarly, the horizontal side of the triangle, the one over here, this has side length x, okay? Because we go to the right x units and up y. So that's exactly what it means to have the coordinates x comma y. That's how we reach there. It's like a roadmap of getting there. And now we have a triangle with side lengths x, y, and 1 for our sides. Like we said, the vertical side is the opposite. The hypotenuse is, of course, 1, because that's opposite the 90-degree angle. So our sine is just y over 1. Or in other words, our sine of theta is equal to y on the unit circle here. And we can do the same thing with the cosine of theta. Well, we've already figured out that the adjacent side here has length x, because we figured out that this side has length x just by the definition of what these coordinates are. We can tell that's right next to the angle, so it's the adjacent side, recalling from last unit. So the adjacent side has length x, and the hypotenuse is, of course, 1 again. Or we figure out that the cosine of theta is equal to x here, right? And similarly, for tangent of theta, it's O over A. Well, we just figured out the opposite side here has length y, and the adjacent side has length x. And what we can figure out from this picture then is that if point P is on the unit circle, we're going to highlight that and make sure we understand this part. If P is a point on the unit circle, you must be on the unit circle for this to be true. Then the coordinates of P are, well, they're x comma y, obviously, but what we just figured out above is that x is equal to the cosine of theta, right? So the coordinates of P are just equal to cosine of theta, and y is equal to the sine of theta, right? But that's only on the unit circle. So we can use that as a sort of quick way of figuring out these side lengths of this triangle here, right? And we can kind of work in both ways. If we know the values of the coordinates, the x comma y, well, then we know cosine of theta is equal to the x, right? If we know the and we know that the sine of theta is equal to y. Or if we happen to know the cosine of the angle, well, then we immediately know what the x coordinate of that point is, right? So let's just take a look at this here. In number 1, it says P is a point on the unit circle, which means what we just said is true. It has coordinates 0.6, that's our x coordinate, as we see over here, comma 0.8, which is our vertical length of this. We want to find sine of theta, cosine of theta, and tangent of theta. But what we just figured out is that sine of theta is equal to the y coordinate, or 0.8, on the unit circle. And cosine of theta is equal to the x coordinate. And the tangent of theta, and this part's actually true regardless if you're on the unit circle or not, but the tangent of theta is always equal to y, 0.8, over 0.6, which we could easily figure out is just 4/3, right? So let's take another example, like problem 3 here. It says if point P, which has coordinates -1/2, comma radical 3 over 2, lies on OP, this line OP here that it's showing us, at the intersection with the unit circle as shown below, then determine the sine of theta, the cosine of theta, and the tangent of theta. Well, it's worded a little differently, but right here it says the line OP, this line here, is on the intersection with the unit circle, which means that point P has to be on the unit circle. That's the only way they could intersect. In that case, then, the sine of theta is just equal to the y coordinate, which here is radical 3 over 2. And the x coordinate, the cosine of theta is equal to the x coordinate, or -1/2. And tangent, again, is equal to y over x, or radical 3 over 2, over -1 over 2, which we can easily handle because we had a whole unit on how to work with complex fractions and lessons therein. And this is just equal to negative radical 3, right? So this whole idea of the unit circle sort of helps us a lot when points are on the unit circle. We can easily figure out the value of the trig functions if we know that we have some point in the coordinate plane like that. One other thing we want to take note of right here that's not important for this lesson so much, but will be in the future, notice that our trig functions are allowed to take negative values. It might seem a little weird to think about because we defined these, and it's true. They are the ratio of side lengths in a right triangle, and side lengths shouldn't be negative, right? But when we're on the coordinate plane, our axes here can be, our coordinates can be, of course, negative, right? We can go to the left and we can go below the x-axis here, right? The idea here is that the right triangle we're talking about is the one that's set up with the point, that's set up by the line that's perpendicular from our point P to, or I should say that is, yeah, perpendicular to the x-axis and over to the y-axis here. And our hypotenuse is always the line that connects the origin to the point there, right? That's the right triangle we're talking about. So again, it sounds a little weird that our trig functions can be negative, but they can take negative values. Not important for us right now, but it will be in the future lessons. So we'll just understand that. For now, we'll just keep working with this unit circle, where again, we've figured out that if we're on the unit circle, sine of theta is just equal to y, cosine of theta is just equal to x, and tangent's always y over x here. But what about if it does not lie on the unit circle here? What's going to happen in that case? Well, let's take a look at something like number 5. It says a point P with coordinates -5, 12 does not lie on the unit circle. Determine the values of sine of theta, cosine of theta, and tangent of theta. Well, we can't just use our simple little trick that sine of theta is going to be equal to y and cosine is going to be equal to x. But what we want to do in these cases is always start out by drawing a little coordinate axes and plot our point, right? So P having coordinate -5, 12 means go to the left 5 units, right? So this length here, -5, and up 12 units, right? And then the triangle that we have always connects this point P to our origin there, right? And in this case, remember, the angles we're talking about, one of the sides is always the positive x-axis, and the terminal side, it's just going to be wherever that ray is. So this is our angle theta here. That's the theta we're trying to figure out in this case. So we need to know then how to figure this out. If this is our angle theta, well, how do we figure out what these values are in that case? We use what's called the reference angle, which we're going to talk about, but we're going to label all of our sides in reference to this little supplementary angle with theta there, in which case the vertical side there is still our opposite, the horizontal side is still the adjacent, and the radius is still the hypotenuse, except at this point, since it's not the unit circle, we don't know what the hypotenuse is, right? So we need to figure out exactly what that value is, but thankfully there is another theorem from trigonometry, and you've learned in geometry regarding triangles, called the Pythagorean theorem, which allows us to find the values of the third side of a triangle knowing the other two, right? And remember, the Pythagorean theorem here tells us that a squared plus b squared is equal to c squared, right? Where a and b are the legs of the triangle and c is always the hypotenuse. So it doesn't matter what you call a and b here. So let's say a is 12 and b is -5. And c is, of course, our hypotenuse, which we don't know here, right? So just working this out, 144 plus 25 is equal to c squared, or 169 is equal to c squared. Taking the square root, we get that 13 is equal to c, right? And yes, you may recall that if we're taking the square root, it should be positive or negative, but we can always just take the positive value here, since we're talking about this radius, which is really just a length exactly from the origin to the point there. So in this case, the hypotenuse is 13. And at this point, we just have another right triangle, and it's easy to figure out exactly what the values of sine, cosine, and tangent are. Sine is always opposite over hypotenuse, or in this case, 12 over 13. And cosine is the adjacent over hypotenuse. But the adjacent here is -5 over 13, because that x coordinate we went to the left, right? Or like we see over here, -5. And it's always important to get that right, to get those signs right, because it's going to affect the value of your trig function, whether it's positive or negative, and that's important. We need to get that right. But getting back to the problem here, the tangent of theta is always SOHCAHTOA opposite over adjacent, which is just 12 over -5, or just -12/5, however you want to write that. Okay. So when the point is not on the unit circle, there's a little bit extra work with the Pythagorean theorem in that case, but it's the same general idea. We always want to sort of set up that triangle that we would have if it was on the unit circle there. We just might have to, in that case, our radius is not equal to 1. We might have to find our hypotenuse. Right, so let's do one more of that, and then that's the end of this lesson here. So it says, if the terminal side of angle A falls in quadrant 2 and tangent of theta equals -3 over 4, determine the values of sine and cosine of that angle. Right, so you might be saying, Mr. Vetta, this doesn't make any sense. This isn't exactly, this isn't like the same problem at all, but really it is. It's giving us the same sort of information we just had here. Right, we just sort of got to break it down. It says, if the terminal side of angle A lies in quadrant 2, right? So quadrant 2 is over here, right? Let's just draw the terminal side in that case. And it says the tangent of theta equals -3 over 4. Find sine and cosine. Whenever we're working with the coordinate plane, we always want to sort of set up that little reference triangle we saw like we would have from the unit circle. So always just draw a line from your point, wherever it is, down to the y-axis. And we also have this triangle here, right? But understand where you are in the coordinate plane. So in this case, we go to the left of the y-axis, which means our x values are negative. This value will have a negative number. We're still above the x-axis, so this is going to have a positive number, right? So it says that the tangent of theta is equal to -3/4, right? And again, this is our little angle theta here, and in this case, that's our angle A. The tangent is always, in our reference triangle, it's always equal to the opposite side over the adjacent. Well, the opposite side in this case is always that vertical angle, or has a value of 3 here, while the adjacent side is the horizontal one, which is a 4. Now, I haven't put in the negative yet, but that we just need to use a little bit of reasoning about where we are in the coordinate plane, which is exactly why I mentioned that. So the 3 is not negative here, but the 4 is, right? The x coordinate is the one that's negative, not the y coordinate, right? And now it's exactly like the problem we just saw. We need to know the value of the hypotenuse in order to solve for sine and cosine, but in order to do that, we're just going to use the Pythagorean theorem, right? Plugging in the values of our legs, 3 squared plus 4 squared. So we have 9 plus 16 should equal c squared, or 25 equals c squared. Taking the square root, we have that 5 is just equal to c. All right, and now we can very easily figure out that sine of theta is equal to O over h, where the opposite side here has value 3. And the hypotenuse we just found has value 5. And the cosine of theta, same idea. It's just adjacent over the hypotenuse, which here is -4 over 5. And it's very important to put that negative sign where it belongs, because the cosine is negative in quadrant 2, and we're going to learn that, but the sine is not, which is why it came out exactly as it did here, okay? So that's our introduction to the unit circle and sort of figuring out trig values from the coordinate plane based on the coordinates of a point in the coordinate plane there. We're going to move on. We're going to use this idea more in our next lesson, so it's important we understand this, right? When we're looking to find exact values in lesson 3, the unit circle and this little reference triangle there is really going to help us out. But that is the end of this lesson. Sorry, this one took a little bit.